Let's talk about the single most important component ever invented. I'm talking about the tiny, tiny switch that powers, well, pretty much everything in our digital world.
Take a look at this number, 100 quadrillion. That's a 1 followed by 17 zeros. It's a number it's almost impossible to wrap your head around. So what in the world are we even looking at here?
Well, that's the estimated number of transistors we have here on Earth. Just think about that for a second. That's more than all the grains of sand on every single beach in the world. These things are the microscopic heartbeats ticking away inside your phone, your car, your computer, you name it. They are, and this is no exaggeration, the fundamental building block of modern civilization.
But what if I told you that the most important component in all of history was actually fundamentally flawed? And that's exactly what we're diving into. See, the story of the transistor isn't about perfection. It's about a brilliant, absolutely elegant compromise that made our entire digital world possible.
All right, so let's start with the basics. What job does this switch even need to do? Well, in the digital world, you need absolute, rock-solid certainty. We need a switch that is either completely on or completely off. There is absolutely no in-between, no kinda on. That simple idea, that's the foundation of all binary logic.
So what does that look like in the world of electronics? It means a component has to grab an output signal and either yank it all the way down to 0 volts, we call that ground, or push it all the way up to the power supply voltage, you'll often see that called VDD. It's got to be a perfect 0 or a perfect 1, no messing around.
So who are our candidates for this critical job? Well, they're transistors. But here's the thing, it's not just one type. We're going to need two very different specialists, and each one has its own unique and kind of limited talent.
All right, let's meet our two contenders. On one side, we've got the NMOS transistor, and on the other, the PMOS transistor. Now, as we're about to see, each one is a total pro at one thing, but neither can handle the whole job alone. You could almost call them our flawed heroes.
Okay, first up, the NMOS. This transistor's superpower is pulling a signal down. It is an absolute expert at yanking an output to ground, giving us that perfect, crisp logic 0. But ask it to do the opposite, to push a signal up to a 1, and it just can't do it. It gets really close, but it gets stuck before reaching the full power supply voltage. It falls short by just a little bit, what we call the threshold voltage. So it ends up creating a pretty weak, kind of mushy 1.
And then we have the PMOS transistor. It's basically the exact opposite of the NMOS. It is fantastic at pulling a signal up. It'll connect the output to the power supply and give you a beautiful, perfect logic 1 all day long. But you guessed it, ask it to pull that signal down to 0 and it fails too. It gets stuck just a little bit above ground, so it passes a weak 0.
So here's the puzzle, right? This is the core engineering problem. We've got one guy who's great at pulling down and another who's great at pulling up, but neither one can give us both, that perfect 0 and that perfect 1. So what do? What's the solution?
And the solution? It is one of the most beautiful, elegant designs in the history of engineering. Instead of trying to fix the flaws in each one, the idea was, why not use them together? Let's create a complementary system where each one's strength perfectly cancels out the other's weakness. And a structure is just genius in how simple it is. Okay, here's what we do. We take the PMOS, our pull-up specialist, and stick it on top. It connects our output to the power supply. Then we take the NMOS, our pull-down expert, and put it on the bottom, connecting the output to ground. And for the final touch, we tie both of their inputs together, so a single signal controls them both.
And this is where the magic happens. Watch this. When the input signal is low, a 0, the PMOS on top turns on, and it yanks the output high to a perfect 1. Meanwhile, the NMOS on the bottom is completely off. Now, what happens when the input goes high, to a 1? The roles totally flip. The NMOS turns on, pulling the output all the way down to a solid 0, while the PMOS on top shuts off. You see? One is always actively working while the other is off. They work in perfect harmony, like a seesaw, guaranteeing a clean, perfect rail-to-rail output every single time.
And that brilliant little circuit, my friends, is the CMOS inverter. CMOS just stands for Complementary Metal Oxide Semiconductor. And since it always outputs the opposite of its input, a low in gives a high out and a high in gives a low out, we call it an inverter. And I'm not exaggerating when I say this is the fundamental atom from which every single modern processor, every memory chip, every digital circuit you can think of is built.
Okay, so that's the theory. We have our logically perfect switch. But The real world is messy. In reality, engineers are constantly juggling this tricky triangle of constraints. How fast can this thing actually switch? How much power does it suck up? And, maybe the biggest question of all, can we actually build billions of these things reliably?
So let's break down each of those challenges. And let's start with speed. Because trying to make our little switch flip-flop billions of times a second, well, that brings up some really fascinating problems.
So here's something that might surprise you. Turns out, the things carrying the charge inside an NMOS transistor, those are electrons, they move about twice as fast as the charge carriers in a PMOS transistor, which are called holes. Think of a hole as just the absence of an electron. So to make the switch equally fast at pulling up as it is at pulling down, engineers have to do something clever. They have to make the slower PMOS transistor physically wider, about twice as wide actually, just to compensate. It's a cool little trick. You create a physical imbalance to achieve perfect electrical balance.
Okay, what about power? Where does all the energy go? Well, most of it is what we call dynamic power. That's just the energy needed to charge up and then discharge all the tiny little wires connecting these transistors together. Then you've got a little bit lost to short circuit power. This happens for a split second when the switch is flipping and both transistors are briefly on at the same time. And finally, there's always a tiny bit of leakage, just a little bit of current that always manages to sneak through even when it's supposed to be off.
And that brings us to the just staggering challenge of reality. Think about it. It's basically impossible to manufacture billions of anything perfectly. Now imagine those things are just a few dozen atoms across. The tiniest little variations in the manufacturing process can have absolutely huge consequences.
Just to give you a sense of the scale we're talking about, a transistor's behavior depends on a very precise number of special impurity atoms, we call them dopants, that are mixed into the silicon. Now, in a modern tiny transistor, there might only be about 100 of these atoms in the most critical area. 100. So if just a few of those are in the wrong spot, the whole transistor's behavior changes. This is a huge headache for chip designers, and it's called random dopant fluctuation.
So, if every single one of the billions of transistors on your chip is just a little bit different, how on earth do you test it? How do you even know if the silicon wafer you just got back from the factory is going to be fast or slow, or maybe just totally broken?
Well, they use this really clever trick. They build what are basically tiny little racetracks for signals. They take an odd number of our inverters, chain them together, and then feed the output of the very last one all the way back to the input of the first. What does this do? It creates a circuit that can't make up its mind. It just oscillates, flipping back and forth forever. And the frequency of that oscillation, that tells you the average speed of the inverters on that part of the chip. So engineers sprinkle these ring oscillators all over the place to get a live report on the health and speed of their silicon. So that brings us full circle. The CMOS inverter, is it a perfect switch? No way. It's built from two specialists that are, on their own, flawed. It needs to be physically lopsided to be electrically balanced. And it's at the mercy of the random chaos of the atomic world. But here's the beautiful part. It's this perfectly managed, brilliant set of compromises that ultimately created the switch that runs our entire world. A perfect compromise.